We've previously defined electric potential, but haven't looked exactly at how to calculate something's electric potential without knowing the electric potential energy. And so that's what this video will introduce you to. We're going to start with an equation that we know from mechanics, mainly that the work, which is equal to the negative change in potential energy, can be found by the integral of the force dotted with dr, where dr is a vector that points in the direction of the movement or between points A and B, whatever points A and B are. So applying this to electrostatics, we're going to focus on the change in electric potential energy, and therefore the force that we use will be the electric force. We also know that the electric field is equal to that electric force divided by the charge. So if we solve for electric force, we get that it's equal to the charge times the electric field. I've plugged that into my equation here. Now, in class, we defined the electric potential difference as the electric potential energy per coulomb of charge, or in other words, delta V is delta UE divided by Q. So if I solve this, or if I include this here, then my potential difference, or delta V, is equal to that negative change in electric potential energy divided by Q, which then is equal to the integral of QE dot dr divided by Q. And so these two Q's would cancel. Therefore, we're left with a general expression that relates the potential difference to the electric field. I've also made this into a definite integral by putting limits from A to B on here, showing that we're looking at the potential difference between 2 points in an electric field, naming those 2 points A and B. This is a general expression that can be used anytime we have an electric field, and we'll study how we can apply this expression with a few different electric fields. The first and simplest electric field that we have studied is the electric field created by point charges. So using this general equation for the electric potential difference, delta V equals the negative integral of E dot dr, and knowing that we have an expression for the magnitude of the electric field, E is equal to KQ over R squared. Again, this is when the electric field is produced by a point charge. We can plug that into our expression to be able to ultimately come up with an expression for the electric potential or electric potential difference due to a point charge. You'll notice that I've also put some limits in there. I said that we're going from infinity to some point R, and infinity is where I'm going to consider to be my reference point, where my electric potential energy is 0. Since if we were infinitely far away from our point charge, that is our source charge, we would not feel any electric force from it. Now, I have also removed the dot product from the expression there because I'm going to assume that my R vector is in the same direction as the electric field. In other words, that I am moving or looking at a path that goes from point R to infinity that is a straight line in line with what the electric field line would look like. If for some reason I was doing the opposite, or let's say that my electric field would be pointing in an opposite direction, I may include a negative sign in that expression. But evaluating that expression, you'll see that we're starting out here by taking the integral, and so the integral of KQ over R squared. Let me change the color here. The integral of KQ over R squared is that negative KQ over R, and I still have the negative sign in right here from the expression itself. So those two negatives would cancel out to become a positive. And I'm evaluating that between R and infinity. And so I'll first plug in R, so I have KQ over R minus KQ over infinity, basically saying that it's minus KQ over some really big number, and that would basically give me 0. So my expression for the change in electric potential, delta V, can be found by doing KQ over R. In this particular scenario, you can plug in a positive or a negative sign for Q. I will also point out that since we're saying that delta V is equal to the V final minus the V initial. Apologize for the bad handwriting on here. And I am kind of saying that at one of those points, it's at infinity, so the V is 0. Sometimes you also see this expression to just say that V equals KQ over R squared, and we call it the electric potential as opposed to the electric potential difference. We will, of course, do lots of practice with applying this and eventually get to the point where we're applying that general expression for the electric potential difference and how it relates to electric field to other examples of electric fields.